All right, today in this session, we're going to talk about backpropagation. First of all, where we are now. I've talked about this quite a lot. To develop an AI model, we generally follow these 5 steps. The first step is data preparation. Of course, you are taking the data-driven approach. Therefore, we need some data to train our models and to test our models. And the second step is after we collect our data set, we need to actually build our models. And there are many multitudes of options we can take. However, we are going to use neural networks, basically, because we are in the era of deep neural networks. And after we design our models or select some models from our options, we need to train our models using our data we collected. And there are 3 steps in training models. And the first one was loss functions. Loss functions was about quantifying how well our models are doing at the moment. And it numerically measures the goodness of our current model. And I mentioned that we are designing our models as a parameterization, which means we have W parameters. However, the values of these parameters can change. In other words, the computational structure is fixed and we receive our input X. However, we can change the output by modifying the values of the parameters. And to change these parameters, we need to come up with some way to quantify the goodness of current values of parameters. And that's what loss functions are doing. And after that, we need to come up with a way to update the values of these parameters. To do so, we need to do something called backpropagation. That's the topic of today. And after that, we are going to follow the process of optimization. And using these 2 processes, we can update the parameters or the values of the parameters. And after that, we evaluate our models. And then if the performance is not satisfactory, we go back to previous steps. If we need more data, we collect more data. If we need to change the model structure, then we redesign our models. Okay, that was where we are at the moment. And these are the contents of today's session. First of all, I'm going to give you some motivation why we need to do backpropagation. And after that, we are going to review some concepts we learned in the calculus class. Some of you might remember how to calculate gradients. However, it's like a few years ago, and you guys need some review, I guess. And after that, we are going to apply the concept of gradients to computation graphs, where we can actually calculate gradients for our complicated models. And then we are going to revisit activation functions, and we are going to see how we can implement our activation functions in line with computation graphs. And then I'm going to summarize this session. Okay, first of all, motivation. This is what we talked about in the last session. We have some data set consisting of X and Y. X is the input, and Y is the expected output. In other words, we sometimes call this value as ground truth. And we came up with the concept of score function. Score function receives the input, and then it is parameterized by W. For example, the output is calculated by the matrix multiplication between W and X. And this score function predicts the score of this input, whether it belongs to a certain class. And if the score prediction is quite good, then it's going to have a low loss. However, it is not behaving as expected, then it's going to cause a lot of loss. And we defined some loss functions, and we had a look at two examples, softmax and SVM. And the third one was regularization. Regularization was to inject our preference towards the weights we prefer. And this is how we formulate our problem. And to find the best values of W, we need a process called backpropagation and gradients and other concepts. And this is what we're going to discuss in this session. Okay, and finding the best values of W is like this. This is a metaphor that I'm giving you. It is like you are blind and you are in the middle of a mountain. And what you want to do is going to the lowest point. However, you cannot see anything. Let's just assume that you are blind. That's the case. That's very similar to what we are doing here. We want to find the values, the optimal values of W. However, we do not know much about the W space. And what we are doing is climbing down this hill without knowing much about the characteristics of this W. And what kind of strategies can you take? The first strategy we could take is random search. What I mean by random search is as follows. We randomly generate W and then check the loss. And if this loss is better than the current best loss, then we update the best loss and best W. And we generate multitudes of W, set of multitudes of W values, and then check whether the new one is better than the previous ones. By doing so, we might be able to find a good W. And when you actually execute this program, it prints out this log. And as you proceed, the loss decreases. However, it's not that satisfactory. So when we actually check how well this approach is doing, it achieves 15.5% accuracy when we are dealing with CIFAR 10 dataset. However, the state-of-the-art performance is approximately 100%. So compared to soda performance, it's far below than soda performance. And another thing is, because there are 10 classes we need to choose, if you just guess the answer, then you might get 10% accuracy. Therefore, 15% is better than a random guess. However, it's not a big improvement. And another strategy we can take is following the slope. So here we are at this position. And what we're going to do is we follow the slope that leads me to lower point. That's what we are going to do in the strategy 2. And how can you do that? In mathematical formulation, slope can be achieved. We can calculate the slope using derivative in one-dimensional space. And you know the definition of derivative at point x. You add, so here is our function f. And let's say this is point x. To calculate the slope, what we are doing is we increment the x value a little bit, like h. And then we just check how much the output value changes. And this is going to be our slope. So we measure this value. So fx plus h minus fx divided by h. And as we take limit and h goes to 0, this one becomes the slope at point x. And this is the definition of derivative. In multiple dimensions, the gradient, the derivative in the multiple dimensions becomes the gradient. And here, the derivative is just a scalar value. However, when you move to multiple dimensions, the gradient becomes a vector along each dimension. And the slope in multiple dimensions in any direction is the dot product of the direction with the gradient. The direction of steepest descent is the negative gradient. So what I mean by this is you can calculate the slope in any direction by taking the dot product of the direction, the slope direction, with the gradient. And the direction of the steepest descent is the negative gradient. Let's have a closer look at what this means in the following slides. And to calculate gradients, we can first take a numerical approach. How can you calculate gradient? What we do is we add a small value to the first dimension and keep the rest of the value as they were. And we'll see how much loss changes. And by using this derivative equation, you can calculate the gradient in one dimension, and it becomes minus 2.5. And we do the same thing for the next dimension. As before, we just check how much loss changed here, and divide the change with the small value we added to that dimension, and it becomes 0.6. And we do the same thing for the rest of the dimensions, and we can calculate numerical gradients. However, the thing is, numerical gradient is very slow. You need to loop over all dimensions. And another disadvantage of numerical gradient is that it is just an approximate value, not the accurate value. So this is very silly. And we know that the loss function or the loss value is just a function of W. We saw these equations and we want to calculate gradient in respect of W. And the loss is calculated using these W values. Therefore, we can calculate gradient in respect of W. And we are going to use calculus, Newton and Leibniz, to compute an analytic gradient. And gradient dW is some function of data and W. I'm going to summarize what we have discussed up to this point. In summary, numerical gradient is an approximate value. It's very slow. However, it's quite easy to write. And another way of calculating gradient, because we wanted to follow the slope to climb down the mountain, we need to use analytic gradient. And analytic gradient is exact and faster because we just use the equation to calculate the gradient. However, the thing is, it's error prone because we make many mistakes when we do math. So if there are some errors in the derivation process, then the whole goes wrong. And what we do in practice is we always use analytic gradient. However, we check our implementation with numerical gradient. So we calculate analytic gradient on our paper, and then check whether our calculation is correct or not using numerical gradient. And this process is called gradient check. And gradient descent is we calculate the gradient of the weights. So we evaluate gradient. We take the derivative of loss function in respect of weights and data. And by performing this update, we move in the negative direction of the gradient. Then we can find better weights that would result in lower loss. Because we are moving in the negative direction, meaning that the slope is positive, then we go to the negative direction. Or if the slope is negative, we just follow the slope. Then our value, xt, let's say wt, and wt plus 1 will achieve lower loss. Because that's what we want to do, lowering the loss. We want to find the values of w that lower the loss. That's what we want to do here. And how do we implement these concepts? So, backward pass of activation. When we're implementing the backward pass of activation, we need to be very careful because we are connecting multiple modules, and these modules can be like 100, more than 100. And if any one of them goes wrong, then the whole system becomes useless. Therefore, you need to be very careful when implementing the backward path. And we could verify via Newton's difference quotient using this one. However, this one could be biased. And what we actually use is symmetric difference quotient, this one. So rather than looking at one direction, we're looking at two directions. So from minus h to plus h. And we're going to see how this affects the result of implementation in the implementation session. And another issue is how do we choose h? When we calculate the gradient, we need to take x plus hf and x minus hx divided by 2h. And we cannot make h goes to 0 because we are using computers, and computers cannot make this limitation correct. Therefore, we need to do some approximation. And what value should we use for h? And here, it states that h equals 0 is not defined. And there is trade-off between rounding error and approximation error. If you make h very small, like this, then computers might not be able to express this number. However, if you make h very big, like 1, then there might be very big approximation error. So there is a trade-off between these two things. And it is known that the good choice of h is cube root of epsilon, with the epsilon, the machine precision. For a 32-bit computer, epsilon is known as 6 times 10 to the power of minus 8. And for double precision computers, like 64-bit computers, it is known that epsilon is 10 to the power of minus 16. And for example, let's see the sigmoid. Sigmoid derivative using symmetric differences with single precision. And this is the analytic gradient we could calculate using pen and pencil. And when we use the value, this one is equal to 1. The maximum error is 0.018. And this is the difference between analytic gradient and numerical gradient. And when we change the value to 10 to the power of minus 4, then the maximum error becomes this, very small, much smaller than the previous case, right? And here you can actually see the difference between the analytic gradient and the numeric gradient. However, in this case, the difference is barely noticeable. However, when we further decrease the value of h, and when we use the value 10 to the power of minus 6, then the maximum error increases like this. And you can see with your own eyes that the analytic gradient and numeric gradient become distinctive like this. So the takeaway message is you just need to use an adequate value for h, which is known as 10 to the power of minus 4. And this phenomenon occurs because computers uses certain bits to express numbers, and it cannot accurately represent all the numbers. Okay. Let's implement this together. The first topic is calculating derivatives. And I told you that numerical difference, let's say this one is naive, we receive the function f and the value x. And let's define h as 10 to the power of minus 15. And we're going to return fx plus h minus fx divided by h. we can implement our numerical difference derivative function like this. However, when we print out what this value becomes, then our computer says it is 0. It cannot distinguish 0 and 10 to the power of minus 50. It cannot distinguish these two values. Therefore, when you put this number, it will say, nah, I can calculate this number. Then how do we implement our numerical differentiation function? As I told you, we better use this value. And another thing is, rather than just calculating the gradient in one direction, we're going to take these values from two different directions. And then we are going to divide this value by 2 times h. So this is going to be the correct implementation.